Hello and welcome to this video on modeling and solving two types of problems, joint variation and combined variation problems. So in this video here I have one example of each where in one quantity is jointly varied or varies jointly with two other quantities. And also I have another example where there's combined variation, meaning that one quantity varies in one way with one quantity and in another way with another quantity. For instance, varies directly with one and inversely with the other, or varies jointly with one and inversely with the other, right? A combined variation. And I'll discuss more about that in a little bit, but we'll have, well, let's just start here with the first example. So my first example, a nice little word problem about something in physics. Got a kinetic energy problem here. And if you're not familiar with physics or the concept of kinetic energy, don't worry so much about it. We're just focusing on what it means for one quantity to vary jointly with a couple other quantities. All right, so notice here I say the kinetic energy represented by the variable k. The kinetic energy K of an object varies jointly with, and then you see two quantities mentioned, its mass and the square of its velocity, right? So mass and velocity, well, the square of its velocity are the two quantities that the kinetic energy vary jointly with. All right, so before I read the rest of that, I'm going to talk on the next page here about what it means for one quantity to vary jointly with multiple other quantities. So here's a page here. Well, let's see. This is on joint variation. All right, so if I have a quantity that I'll call A, so a quantity, again, say just capital A here, varies jointly right, so it varies jointly with several other quantities. Right, so varies jointly with several other quantities if A varies directly with the product of those quantities. So we have to remember what it means to vary directly with a variable. Right? Varies directly with the product of those quantities. So in other words, if I were writing out a little equation here, that would mean that A is equal to, now remember what it means to vary directly. I put up a video a couple videos back. Hopefully you watched it. If not, just explain it really quickly here. If one quantity varies directly with another quantity, that means that that one quantity is some constant multiple of the other. So if I say that A varies jointly with several other quantities, that means that A is equal to some non-zero constant, right? This letter K here is a constant, and that's going to be referred to as the constant of proportionality. Okay. So A varies jointly with several other quantities means that A varies directly with the product of those quantities, or A equals to some constant multiplied by the product of these other quantities. So say I have the quantities B and C. Okay, so there's K times B times C. All right, the way this is written right here, I would say that A is jointly proportional with, or varies jointly with, B and C. And so this statement in the box I have here is telling me that A is jointly proportional with, or varies jointly with B and with quantities B and C. Okay, so that's all it means. And if I said that A varies jointly with B, C, and D, then you'd have A being equal to some constant times the product of B, C, and D. Right, you can throw on as many quantities as you wish to this product on the other side with the constant of proportionality. All right, so keeping this in mind, let me go back to my problem. All right, I'm going to keep the little model up for what it means for one quantity to vary jointly with two others. And the very first sentence, right, I'm stating that the kinetic energy, right, represented by K, capital K, right. So I'm going to try my best to make a capital K and lowercase k look different. Let's try to pay attention. All right, so the kinetic energy of an object varies jointly with its mass and the square of its velocity. All right, so I'm going to call these quantities something. Well, so I've got some unknowns here. One thing is the mass of an object. All right, so I'll call that something. Let's say the mass. And usually mass, if you're reading a physics textbook or math textbook, is represented by a lowercase m. And this I noticed when you read through later, the kinetic energy of 110 kilogram linebacker, 140 kilogram linebacker later. It looks like the mass is given in kilograms, right, or that kg. So all my masses of objects are in kilograms, and and the square of its velocity. All right, so velocity usually is represented by just a lowercase v. And what are the units on that? Well, look at the velocities at which these linebackers are running in the next couple sentences. The kinetic energy of a 110 kilogram linebacker running at 9 meters per second, running at that velocity. Same thing later, I'm seeing running at 5 meters per second at the end. So it looks like the velocity units are in meters per second. Right, or I can do a meters per second like that. And then again, I can just do kg for kilograms. Okay. And the kinetic energy I've already stated was the letter K. Again, a capital K. And that's in what are called joules, right? Energy's in joules here. They say the kinetic energy of a 110 kilogram linebacker running at 9 meters per second is 4,455 joules, which you'll see as just like a capital J sometimes in books. I might just write out the word joules for energy. All right, and we're told that the kinetic energy varies jointly with its mass and the square of its velocity. So not just its velocity, but the square of the velocity. So the velocity squared. All right, so I'll write that out in words over here. So again, we say I'll say capital K here. The kinetic energy varies jointly with mass m and the square of its velocity. So not just the velocity v, but the square of its velocity, v squared. All right, let me write an equation there. like I have down here in the box, in the blue box down here, when I talked about what it means for one quantity to vary jointly with two others. That means that we can write an equation like this, that the kinetic energy, in capital K, is equal to some constant, right, a lowercase k, right, and try to make definitely a lowercase k. And you can call it another letter if you wish, like a little c for constant or something. But again, I'm trying to stick to what you're typically going to see in a physics textbook or a math textbook. So the capital K, kinetic energy, is equal to some constant, some lowercase number k, multiplied by then the product of the mass and the square of the velocity. Okay, and so now we have this set up. Right, the kinetic energy is varying jointly with the mass and the square of the velocity. But just like in my previous videos on direct variation and inverse variation, right, this equation is not complete because these are variables, the k, the m, the v, those will change. But this k, this is a constant, right? This lowercase k here is a constant. I need to find this value to be able to complete the equation. And in order to do that, I'm going to have to use some information that was provided to us in the problem. All right, so let's look back through the problem. All right, so they told us in the first sentence, the kinetic energy K of an object varies jointly with its mass and its square of its velocity. I have stated that here. The next sentence gives me the information I need, all right, to find this lowercase k, to find the constant of proportionality. They're saying the kinetic energy of a 110 kilogram linebacker, right? So that's mass. Right, I mentioned mass is in kilograms. Running at 9 meters per second, that is velocity, right, in meters per second, is 4,455 joules. That's the kinetic energy, the capital K. Right? I'll put Ke for kinetic energy, but capital K. Right? So I have some numbers to plug in here, right? I can replace, so in this equation I've set up, this model, I replace, the capital K, the kinetic energy, with the 4,455 joules, the mass, the lowercase m, with the 110 kilograms, and the velocity, the v, with 9, right, the 9 meters per second. And we'll have all the missing pieces in here except for the lowercase k, and then I can solve for that. All right, so let's see what that looks like. So I replace, let's take this over here, replace the k with the 4,445 joules. So I'm in this equation, 4,455 on the left equals, and then the lowercase k, right, the constant of proportionality that I don't know yet, times, and then the mass of this linebacker, they said, was 110 kilograms, and then times, and then the velocity of this linebacker squared. Right, so 9 meters per second squared, so times 9 squared. Okay. All right, so multiplying this out, 9 squared is 81, and then 81 times 11 would be 891, and throw a 0 on that. We got 4,455 on the left, and then as I said, 9 squared is 81. 81 times 110 would be 8,910. Then you have still times this lowercase k. All right, and then let me double check here with just doing a calc. Yeah, it's definitely 8,910. And then to solve for k, right, need to divide by this 8,910 on both sides. Okay, and then, so there's the value of k. Right? This lowercase k, the constant of proportionality, is 4,455 divided by 8,910. And I'm going to put that in the calculator again. All right, now we could also reduce that fraction. Oh, and that's just a half, silly me. This is, if you double 4,455, that is 8,910. Wow, can't believe I didn't see that. Sorry about that. Yeah, this is just a half. This reduces to simply 1/2. And now that I have found the value of this constant of proportionality, this lowercase k here, we can complete the equation. All right. So here's our model for this particular problem. All right, the equation describing this situation. The kinetic energy, capital K, varies jointly with the mass and the square of the velocity, and the constant of proportionality we have found is 1/2. All right, so the kinetic energy of an object is equal to half the product of its mass and the square of its velocity. All right, so I'm gonna bubble this. This is huge. Okay, this is the equation we are going to use to answer any question that may be asked. And then looking back at the problem, the only thing that was asked of us here. Let me slide this back down now. There's the problem. We're using this model. Look at what they're asking us to do. Now the last sentence, determine the kinetic energy. So they don't know K, right? So this is saying, what's the value of K, right? Determine the kinetic energy of a 140 kilogram linebacker, right? So this is telling me that the mass, right, is 140. Right? They're giving me a value of m, running at 5 meters per second. So that's a velocity, and it's got the same units as my other velocity. And so they're telling me that the value of v is 5. Right? So I go to my equation here, and they've given me a value of m. They've given me a value of v, a mass and a velocity. So I pop those in, and we can find this, what's the kinetic energy of such a linebacker, such a person. All right, so putting those in, I have k on the left equals 1/2 times, the mass is the 140 kilograms, times, and then the velocity is 5, but that's being squared. And don't forget, you square things, you do things with exponents first, right before you do your multiplication and division. Okay, so simplifying this, this is half times 40, 140, sorry, 140, 140 kilograms. Then the velocity squared, that's 25. All right, and then we multiply here. Now half of 40 is 70, and then 70 times 25. Well, you can just do 7 times 25, which would be 175, and then add a 0. All right, so 1750. So we're getting a kinetic energy equal to 1,750. And remember the units on this, right? I mentioned it earlier. They gave me units here. The units on kinetic energy is in this joules, right? But I'm going to actually answer the question in a complete sentence. You should have it, when you go through and answer word problems, application problems, you should answer in complete sentences and throw units on your numbers to give them meaning, in the context of the problem. So the way I'm going to answer this question is with again a complete sentence. So the way I'm going to answer this is the kinetic energy of this linebacker, or you could write the whole thing. The kinetic energy of a 140 kilogram linebacker running at 5 meters per second is, but I'm just going to save on a little writing here. The kinetic energy of this linebacker is 1,750 joules. And you can write the word joules out, or just put the capital J for the abbreviation for joules. And there you go. That's how I would answer it if I was given this in an exercise set or as part of a test. Okay. Yeah. but we have, again, the setup is K was jointly proportional with the mass and the square of the velocity, or very jointly with the mass and the square of velocity. So you had K equals some constant times the mass and the square of the velocity, and then you use some information to find that constant, which we found was a half here, and then then use that model, use that equation to solve whatever they want you to solve. All right, so that was an example of one quantity being varying jointly with a couple other quantities. My next example is an example of combined variation, a combined variation problem. And let me actually just talk about that right now before I put the problem up. All right, so here's a little page on combined variation. All right, so this is, again, it's in the wording. When I say we have combined variation, that means there's a mixture of two types of variation. So I think it's best put if you see some examples. If I said y equals k times x and then divided by z, where k is, again, the constant. I'll just say k equals the constant of proportionality, or a constant here. They would say that there's combined variation here. We would say that y is equal to, you got a constant times a variable, so that's direct variation. Right, so y is directly proportional to x, right? Because you have that y equal to a constant times a variable times x. But you also have this, constant divided by a variable going on here too. So it's directly proportional to x and inversely proportional, right? Remember when you have the constant divided by a quantity, there's inverse variation, and inversely proportional, or varies inversely to z, right? But you see how there's two different types of variation going on here, right? There's a mixture of the two. That's what they mean by combined. It's like two put together, two different types of variation going on in the same equation. Another example of this, there I mixed direct variation and inverse variation. Said y equals, k times x times z, the product of x and z here, divided by, let's go, r squared. So again, look at the numerator. We have y equals, and again, k is a constant still. Right? K is that constant of proportionality. You have y equals, and then you see this, you have a constant times the product of two variables, product of two quantities. So this is what we just saw earlier in this video, that's joint variation. So in this example, y varies jointly with, the product of x and z, right? With x and z, and not only does y vary jointly with those two variables, but again you're seeing I have the constant divided by another quantity. So there's also that inverse variation. So y varies jointly with x and z, and y also varies inversely with the quantity in the denominator, which is not just r, but the square of r, right? With r squared. Or you could write out the square of r, like we had with the square of the velocity in the first example from this video. But again, you're seeing the combined variation, right? There's varying jointly combined with varying inversely. So it makes it a little more of a complicated equation, but you're putting two together, two types of variation together in the same equation. thus combined. All right. Okay, so keeping that in mind, all right, let's look at this next problem. All right, another word problem here for you. I have the electrical, so another little physics problem or electricity problem. And if you're not familiar with this stuff, don't worry about it. We're just going to be using the concepts. Just keep track of the units and what letter means what. You don't really have to know anything about electronics to be able to do this. Alright, so I have the electrical resistance called R, right? So R represents resistance or electrical resistance of a wire. The resistance of a wire varies directly with the length L, right? So L represents the length of the wire, and inversely, so see that you got combined variation, right? Not only does R vary directly with L, but it also varies inversely with the square of the diameter, and the diameter of the wire is D. Alright, now I'll draw a little picture of a thin wire here. So you got one end of the wire, and then like a little wormy thing. Let's say that's a wire, and then it's circular and stuff. So here's like a wire, right? Its length would be, how long it is. Right, how long is the wire when you straighten it? Right, L represents length here. The diameter, and perhaps I should have made this, if I blow this up a bit, is at the end of the wire, the circle, one of the circular ends. The diameter of the wire is just how long across that is. If you go across that circle, that distance there, that's lowercase d, that's the diameter of the wire, d. Okay, and again, resistance, not going to really get into what that means. All right, just know that every wire, if there's electricity going through it, has some sort of resistance associated with it, which is going to be labeled by R. All right, so let's write this out. Now this varies directly and inversely, is like my first example here, where you see y varied directly with x. Right, you have the k times x, and inversely with z, because you have the k divided by z. All right, so let's keep that in mind and say, hey, the resistance R, so I'll have R on one side, equals, varies directly with the length of the wire, so equals, some constant k, and again, that lowercase k is the constant of proportionality, times the length of the wire L, right? That's in the numerator. That's resistance varying directly with the length of the wire, and inversely with the square of the diameter. Again, there's that word square again. So not just with the diameter d, but with d squared. And so R varies inversely with d squared. So we'd have the constant again k, and then divided by the diameter squared. So this is a setup for my equation involving the relationship between R, L, and D, the resistance, the length, and diameter of this wire. All right, and as with the previous example, this equation is not complete because I do not know the value of K. Now the R, the L, and the D, those will change all the time. Those are the variables. This K will not change, right? This is a constant, and I must find it. Right? I must find this value in order to complete the equation, find K. And just like the last example, I'm going to use information given to me from this problem to help me find this K and complete the equation. Alright, so reading back through, did the first sentence already establish this relationship? R varies directly with L and inversely with D squared, the square of the diameter. In the next sentence, if a wire that is 432 feet long and 4 millimeters in diameter has a resistance of 1.24 ohms, find the resistance in a wire that has 282 feet long with a diameter of 3 millimeters. Okay, so that information, so forget the part where they ask us to find something right before that. If a wire that's 432 feet long and 4 millimeters in diameter has resistance of 1.24 ohms, they gave us three numbers for these three variables. So they gave us, the length of the wire. They said it was 432, and they're telling us length. They're basically giving us the units. The length is going to be in feet, right? But I'm just going to put 432 in for L. They told us the diameter, right? 4 millimeters. They told us the diameter of the wire, so that's that lowercase d was 4 millimeters, right? So that tells me the units of the diameter throughout this problem. They'll be in millimeters. So whenever I see another diameter, it better be in millimeters, right? And they also told me resistance, right? Has a resistance of 1.24 ohms, right? And so that's the units on resistance throughout this problem. And you can abbreviate these with FT for feet and MM for millimeters. And ohms is actually the Greek letter omega. It's like this weird looking thing here. You might have seen it before. That's a symbolism for, if you ever see it in a textbook, you might, so you know what that means. If it's in a physics book or electronics, this means, ohms, and they're talking about resistance, the Greek letter omega. Okay, well, again, you don't need to know those abbreviations. I'll just write them out in words. It doesn't matter, right? That's not the point of this example. All right, so what we're doing is using this information now to figure out what the constant K is, and then I can complete the equation. All right. So I've got all this information. I'll just pop those into my variables. So the resistance we know is 1.24 ohms, 1.24 on the left side, equals, the value of K that I don't know, times L times, 432 feet, or just, 432, divided by, and then 4 squared, right? The diameter squared in the denominator there, right? The diameter being 4 millimeters. Okay. Now we could try to simplify this side over here. 4 squared is 16. And, this is K times 432 divided by 16. And then you could do take out a factor of 2. 4 would go into each of these. In fact, 16 does go into 432 evenly. Do a little division there. That's 27. 16 goes into 432 27 times. So this is actually just 27 times K, or K times 27. Alright, so I have 1.24 ohms equals, and then over here 27 times K. And then we solve for our lowercase k there by simply dividing both sides by the 27. Alright, so we have K. The value of K is 1.24 divided by 27. Now let's see if I can simplify that a bit. I'll punch that in the calculator, see what pops up. I know it's kind of cheating, but hey, if you got it, use it, right? And that's actually some pretty insane decimal. It's 0.0459259259259. If I convert that to a nice simplified fraction, this is 31 over 675, 31 675ths, and as I said, in the decimal form it's 0.045925. Then it looks like 259. Looks like that the 259 is repeating, and my calculator is only going out to that many decimal places, but it looks like the 259 is repeating. So let's go dot dot dot. That's going on further and it goes on forever. I'm just going to leave it this way though, as this nice simplified fraction. Okay, so now I can complete the equation, replacing k with this fraction here. And we get our equation describing the relationship between resistance and the length of these wire and the diameter of the wire. So the resistance equals, I've got 31 675ths times L in the numerator divided by, and then d squared in the denominator. And if you don't like having what this is called a complex fraction, right, I can get rid of that denominator of 675 by multiplying the numerator and denominator by 675. Alright, so that gives us a nice, the 675s up there would cancel, and I get this final equation here. So the resistance equals, the 675s would go up here, leaving me with 31 times L, 31 times the length of the wire, divided by, and then you just have 675 times d squared in the denominator. So this equation right here is the relationship between resistance, length, and diameter. Great. And now that I have this equation, we can punch in our values. Now notice I didn't round. I didn't use like 0.04 or 0.05. I didn't round the value of k. The reason for that is because they asked me to round the answer at the end. I'm asked to round my answer to 2 decimal places when I find this resistance. And the more you round throughout a problem, the worse the accuracy gets. So I like to keep numbers exact, keep numbers the way they are, the way they should be, until the very end, and then round at the end if I'm asked to round. That way I'll keep more and more accuracy throughout the problem. Alright, just a personal preference. Now if you round throughout the whole problem, yeah, the accuracy will be off, but probably not by that much. Alright, now let's see what we're asked to do. I use this information up here to if a wire is 432 feet long, 4 millimeters in diameter, has a resistance of 1.24 ohms. I use that information to help me get this equation here. Now, what are we asked to do with it? Well, that's the last part. Find the resistance. So they don't know what R is, right? What's R, right? Find the resistance in a wire that is 282 feet, still in feet long. That would be the value of L, right? The 282 feet, with a diameter of 3, and then still in millimeters, the diameter, that's the value of D, 3 millimeters. And round your answer to 2 decimal places, the nearest hundredth. Okay, so I'm just going in here, replacing L, right, with 282 feet, and the diameter with 3 millimeters, and we'll see what the resistance ends up being. Right. So we have the resistance equals 31 times, and then the length, as I said, was 282 feet. So 282 divided by, and then 675 in the denominator here, times the diameter was 3 millimeters squared. All right. So the numerator, right, 31 times 282. I'm going to just punch in this in real quick. The numerator is 8,742 divided by the denominator. You do 3 squared first as 9, and then 675 times 9 is 6,075. All right, and I'll divide these. 8,742 divided by 6,075, and it's giving me 1.43901234 and that would go on forever. Right now, it's going to repeat at some point because this is a rational number, right? Integer over integer. But we're asked to round to 2 decimal places. So remember what that means, the nearest hundredth. So there's the first decimal place, the second, after the decimal point, that's the hundredth place. So to round to the nearest second decimal place, the nearest hundredth, right, I go to the third decimal place. Look at that. And if that's 5 or greater, you bump up the second decimal place by 1. If it's less than 5, you keep the second decimal place the way it is. And this is definitely 5 or greater. It's 9, right? Definitely 5 or greater. So the resistance R is approximately equal to, notice it's equal, but because I'm rounding, I'm going to use this little wavy equal sign. This is approximately equal to 1.4, and as I said, this is above 5 in the third decimal place, so I'm going to bump the second decimal place up to 4. Okay. Now, what are the units on this? Remember, this is ohms. Okay. But like I did in the first part of my first example, when I answer a question in a word problem, I want the question answered in a complete sentence where units are attached to numbers to give them meaning. So back to what we were asked for, they said find the resistance in this wire, that is 282 feet long with a diameter of 3 millimeters. The way I would answer this question is the resistance in that wire, right? Or you could say the whole thing, write out the resistance in a wire that is 282 feet long with a diameter of 3 millimeters is, but I'll just say the resistance in that particular wire, that wire is approximately, but you don't need to use approximately because notice they just said is 1.24 ohms earlier. So let's just use our number here, our rounded number, 1.44 ohms, right? The units on resistance. Okay. And nice complete sentence, and any number that pops up in the sentence has units attached, right? 1.44 has ohms on it to give that number meaning with regard to the problem. All right. But yeah, so hopefully you took away from that what it meant to be jointly varied, right? And also what it meant to have combined variation. Right? That means there was a mixture of two, direct variation and inverse, or jointly and inverse. Right? There was some sort of mixture of the variations that were talked about earlier in this video, and also in other videos I've put up if you want to look those up. Okay, and as I like to say at the end of these videos, do the best you can, try the best you can to learn the material on your own before you go to looking for help. Because I find that people who put the time and the effort in to learn things on their own tend to remember those things for a lot longer and have a better recall of them. So obviously read through the material, read through the author's examples, perhaps even work on an author's examples before you look at how the author did them, and compare your work to the author's and see if you can learn from some mistakes there. Obviously, work on plenty of exercises, practice problems, look up solutions whenever they're made available so you can check yourself to see how you're doing. And don't just give up on a problem after the first attempt. There's very often several ways, several approaches that work in solving a math problem. So if after several approaches at a problem you're still not getting how to do it, or still not understanding the material or what's going on, perhaps you should try reading the material again, maybe even a third time, more slowly, more deliberately. Take notes, because if you've done some problems or even tried to work on some problems after the first read through, you'll have a better understanding, or at least a better notion as to what the author is asking of you, what the author wants from you. And then going back and reading again, you'll know better what to look for, and you'll probably catch some things that second or third read through that you didn't the first time. And it'll make it that much easier. But if after that, if after several read-throughs of the material, several approaches at problems, attempts at problems, and you're still not getting it, it's still not making sense, well then it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. Ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos on the subject. Lots of those too. Videos like this one, or I assure you, plenty of other ones out there that are better than mine. and you can pretty easily find them. But just, keep at it. Stay persistent. Don't give up. Keep practicing. And I think the hardest part is to try to have a positive attitude about the subject. Go in with an open mind, thinking that I'm going to read this today, I'm going to write this today, I'm going to learn something today, and it's going to be good. I'm going to take something away from it. I might even have some fun doing it. I know that's hard. I know that's easier said than done, but it is amazing. You'll be amazed at the difference in, a little tweak in attitude, a little change in your mindset can make to a learning experience. So please, stay persistent, keep practicing, stay positive, don't give up, and I believe and I know you'll eventually get it. Thank you for watching.